is CORDIScovery. Hello and welcome to this episode of CORDIScovery with me, Abigail Acton. Today we're delving into planetary dynamics. So if you feel space research is all above your head, you're in the right place. In this episode of CORDIScovery, our three guests will explain how their work is helping to broaden our understanding of the origins of life, the swirling dust storms in the Martian atmosphere, and how to venture to far distant asteroids. We'll be talking about how life on Earth might have begun, and whether that could inform our research into the possibility of early life on Mars. Dust. There's a lot of it on and above Mars. What role did it play in the loss of Martian atmosphere in the distant past? And, right now, how is it impacting on our interpretation of remote sensor data? And we'll be discussing missions beyond Mars to asteroids. How do space scientists seem to manage the impossible? Back in 2018, a Japanese mission landed 2 rovers on an asteroid 400 meters wide, over 300 million kilometers from Earth. Now, if you've had trouble backing into a garage, ponder on that one. So what's the latest on designing and operating deep space missions to asteroids, and how can we model, track, and collect asteroid fragments? Is it time to start eyeing up asteroid mining startups? Here to talk about these fascinating subjects with me are Fuen Cañadas, a geochemist who works as a research scientist at the Center for Astrobiology in Spain. Fuen is interested in reconstructing the environmental conditions of the Earth's early development, with a particular emphasis on the phosphorus-carbon cycle as a way of improving our understanding of the co-evolution of the environment and life. Welcome, Fuen.
Hi, everyone. Thanks, Abigail, for the invitation. I'm very glad to be here in this podcast today.
We're very happy to have you, Fuen. Thank you. Anne-Carine van Daal works at the Royal Belgian Institute for Space Aeronomy. She has been involved in the design and operation of instruments for the remote sensing of planetary atmospheres and is particularly interested in the role of clouds and dust in their composition. Welcome, Anne.
Hi, everybody. I'm really delighted to be here today.
We're very happy to have you. Thank you, Anne. Mirko Trisolini is an astrodynamics specialist at Vioma, a German company which works on understanding and effectively managing space traffic. He's particularly interested in the study of the dynamics of small particles and techniques designed to collect them from asteroids and other small bodies in the solar system. Hi, Mirko.
Hello, everyone. Thank you, Abigail, and thank you, everybody, for having me here.
Wonderful. Let's start. I'm going to turn to Fuen first. The Mars Phosphorus and Life project asks 2 fundamental questions. How did life on Earth begin? And did Mars ever host life? So no pressure then, Fuen. Can you tell us how and where we think life originated on Earth?
Well, it's a very good question to start because the answer is no. We don't know when and how life originated on Earth. We don't know exactly how. There are a few ideas. So traditionally, places like, for example, hydrothermal vents in the ocean or places with very acidic have been usually proposed as very good spots for life to start because those environments are very rich in nutrients. But those environments have a problem with phosphorus, and phosphorus is a key element for life. We can't imagine life without phosphorus. And in those environments, what happens is that phosphorus is generally trapped in minerals, principally a mineral called apatite, and then the concentration in the water is very, very low. And then it makes the situation very, very limited for life to emerge. So this is what in astrobiology we know as the phosphate problem. However, there is another type of environment that is very popular in the last years, that is carbonate-rich lakes, that might solve this issue. Because apatite, this mineral that I said before, is a mineral that contains both calcium and phosphorus. But in this type of lakes, calcium tends to bond with carbonates instead of forming apatite. So it means that calcium is locked up in minerals, and then it stops apatite from forming. So as a result, phosphorus doesn't get trapped in apatite, and it means that it's available in the water in higher concentrations for life. So this makes these environments, these carbonate-rich lakes, a potential place for life where life could have started. So what I find very, very interesting is here on Earth, many carbonate lakes were formed because of photosynthesis. They are a result of this process, photosynthesis.
That's interesting, Fuen. Thank you very much. So what exactly is the relationship between the carbonate lakes and photosynthesis? What's the role of photosynthesis in this?
Well, on Earth, many carbonate lakes have been formed because of this photosynthesis process. In this case, microbes use carbon dioxide as a source of energy and take it from the water. And then it changes the water chemistry towards more alkaline conditions. And then with higher pH in the water allows the precipitation. These conditions allow the precipitation of carbonate minerals on Earth.
Okay, fantastic. Thank you. That's super well explained. Very much appreciated. So what did Maple do to explore this theory? What was the work that your project did here?
Well, Maple was a very, very exciting project that gave me the opportunity to travel to Thunder Bay in Canada and work in one of the oldest regions on Earth. I investigated rock samples that were from, as I said, 3 billion years ago. So these samples are significant, not only because of their age, but also those are special because they come from the oldest known carbonate platform on Earth. This platform contains stromatolites that are sedimentary structures that have been formed by cyanobacteria, what indicates that life existed there at some point. And these samples were collected from a drill core, which helps preserve the original geological and chemical properties of the rock compared to outcrops.
Wonderful. So, I mean, when you say a drill core, what are the challenges actually of using the drill core to extract these samples? That must have been really quite complex.
Well, actually, the drill core was donated by a mining company. It's very usual in science to work with drill cores that have been drilled before. So we are really, really happy because we had this opportunity. But when working with such old samples, with such ancient materials, we have two major challenges. First, potential contamination of the samples. And to avoid this, we carefully prepare the samples in the lab. We wash them with solvents, remove altered parts, and then cross them very, very carefully, cleaning the mortar after each use to prevent cross-contamination. But also, a second important challenge is diagenetic modifications. And this refers to chemical or physical changes that can happen on the rock over time. And they changes can alter the original composition of the rock. And this is very important because when we are talking about 3 billion year old rocks, we need to know if the results we are getting from our analysis are representing original conditions when their rocks were deposited, or they are representing something much modern, much in the present, for example.
And how do you go about differentiating that? How can you be sure that you are looking at something that is contemporaneous with the period that you're studying?
Well, there in geochemistry, we work with different geochemical proxies, and then we can reconstruct with isotopes or with the analysis of bulk geochemical analysis. We can reconstruct how were, for example, the levels of oxygen in the atmosphere or in the water column, the levels of iron, the levels, and then you compare your results with this analysis, and then you can see because throughout the geological ages, we can clearly see different geochemical fingerprints that belong to the different geochemical periods. So it's quite important. Yeah, it's critical to understand what we are reading.
No, absolutely, because you could go completely on the wrong track. So when you're looking at these sediments, you can see through your various forms of analyses, as you say, fingerprints, I like that word, fingerprints that show specific characteristics of specific epochs. And so you know what you're looking at exactly. Fantastic, super. And what did you find?
Well, when I started working on this project, one interesting question that I wonder myself is how these cyanobacteria that ultimately form the stromatolites were able to emerge and thrive in an environment 3 billion years ago, where the water was anoxic, means with no oxygen at all, and also the atmosphere was rich in CO2, in carbon dioxide. So how cyanobacteria that are photosynthetic organisms were able to evolve? So through this project, through the MAPPLE project, we reconstructed the environmental conditions from this area 3 billion years ago, and we identify periods of oxygen-rich waters within this anoxic environment. So we believe that this oxygen was produced by cyanobacteria that thrived in that area thanks to a higher phosphorus content in the water column, in the water that was present.
And then we come a full circle back to the idea of the importance of phosphorus and the fact that the phosphorus was present, permitting that.
Exactly.
That's fantastic. And tell me, how does this tie into your ideas with regards to the possibility of very, very, very long distant life on Mars? I know that you are very interested in certain calcium lakes that are being looked at by the Mars rover. Can you tell us a bit more about that?
Yeah, sure. Well, the principal hypothesis is that this photosynthetic activity in that area in Canada favored the precipitation of carbonates, and then the formation of this platform where these stromatolites are preserved today. So this is where the story becomes even more intriguing, because we can connect it with Mars. So when life emerged on Earth, conditions were very similar on Mars, with liquid water and anoxic waters, and also a carbon dioxide-rich atmosphere. However, on Earth, there were some, let's say, restricted areas where conditions favored the appearance of life. But what happens on Mars? What about Mars? So carbonates there on Mars are very, very rare. And the reason for this is not very well understood yet. So, for example, acidic conditions on Mars could have inhibited carbonate to precipitate, but also on Earth, conditions were acidic. And life emerged in those isolated areas. So then, what about if then I wonder with my team, what about if the formation of those carbonates on Mars was influenced by life, like many places here on Earth?
So you're sort of turning it around there.
Yeah, exactly.
They are fascinating. So it's not that the carbonate environments gave rise to life because they were favorable, but maybe they were caused by life.
Exactly. This is just an idea. This is the idea that we are developing, and it's very difficult to answer. And to me, I absolutely believe that this interesting question may be answered through the Mars Sample Return Mission, which is the most ambitious mission that NASA has ever had.
So that's NASA's mission to bring back, as it says, samples from Mars.
Exactly. Yeah.
Fantastic.
And currently, the mission, the Perseverance rover that is now on Mars, is collecting rock samples from the Jezero crater. And this crater is special because it's one of the few spots on Mars where carbonates have been identified.
Well, that sounds fascinating. So you don't know what's around the corner. And if you get your chance to have a look at some of the samples that come back, if that works out for you, because I know that you are very keen, I'm sure not alone, to get your hands on some of those samples, you might be proved right, Fuen. Wouldn't that be fantastic?
Yeah.
That would be amazing. Wow, there you go. It's brilliant. Thank you so much. And you really brought that to life for us. I'm very appreciative. Does anyone have any questions for Fuen? Yes, Mirko.
Yes, thank you, Abigail. I was wondering that where you were mentioning about this connection between Earth and Mars, if, for example, when collecting the samples of Mars, they have been exposed to a lot of radiation, for example, so the radiation environment would be much harsher. Would it have some consequences in when you analyze and you compare these samples with Earth?
Yeah, of course, the comparison between the Mars and the Earth has some limitations, and one of them, one very important, is the one that you mentioned, is the surface of Mars has been exposed for millions of years to high doses of radiation. But this is why here on Earth, one part of our analysis is to compare samples from for example, this area in Canada. We use them as an analog. And then we use them and we run or perform different analyses. And then we perform the same analysis once those samples have been radiated in laboratories. And then we can get different signatures, and then we can compare to get a more reliable signature of the data that is coming from Mars.
So to just basically to get closer to what is actually probably going to be coming back.
Yeah.
Thank you very much. It was an excellent question, Mirko. Thank you so much. Thank you. I'm going to turn to Anne now. Anne, the Roadmap project wanted to establish the impact of dust on the Martian atmosphere. Why is it so necessary to gain a better understanding of the role of dust and clouds over Mars, please, Anne?
Yes, thank you, Abigail. It's quite important to understand the role of dust and clouds on Mars, but in fact on any planet it's as important. Because dust and clouds are impacting the atmosphere in many aspects. So, for example, they are constraining the water cycle. They are impacting radiative processes occurring in the atmosphere. So the way the solar radiation, for example, interacts with the atmosphere. And they even impact the circulation, so the way air masses are moving around. We have shown recently that it also impacts on the long-term evolution of the atmosphere of the planet, because more dust on Mars was linked to a larger escape of hydrogen, which is an element of the atmosphere. And so we could show the link between dust and losing an atmosphere.
Right, fascinating. And I believe, of course, it also has an impact on how we observe planets, how we interpret data from our remote observations. Can you tell me a little bit more about that?
Yes, indeed. And that's also another aspect that was studied during the roadmap project, was the impact of dust and clouds on the investigation and the analysis of the data recorded by sounding instruments. So usually the atmospheres are sounded using spectroscopy. And so you will use a fingerprint, as we mentioned earlier, that is really giving information on the presence of a gas and how much there is of this gas. But of course, dust and clouds also have fingerprints, which are overlapping the features shown by atmospheric gases. So in order to get to the abundances of the gases, you must first have a very good idea how much dust and clouds there are.
Yeah, no, I get that totally. So in order to be able to look for what you actually want to be looking at, you need to be able to filter out the noise, the interference that's coming from these extra masses that are circulating around. And that's fascinating. It's obvious when you say it, but it's one of those things that doesn't immediately come to mind. And I suppose this might actually even have implications for the safety of future missions, because if you're trying to determine atmospheric properties, that connects directly with programming of various space machinery and vehicles. No, is that true?
Yes, and this is in fact very important for the exploration of Mars, because dust in fact is present on the planet everywhere, every time. And on top of that, sometimes dust storms can evolve. We still don't know why and how, and they can even evolve into global dust storms, so completely surrounding the planet. And you do not want to land something on the planet when there is such storms. So we need to get more information on the storms themselves, on the dust, to have an idea how the storms can be created and when it is better to try to get there.
Yeah, so the nature of the origin of the storm and whether there's a kind of predictability to them that can be factored in. Yeah, no, I get that totally. We've been thinking a little bit with Fwen just now about the notion of analogs. I find this fascinating. I mean, the areas that you chaps are researching are so very, very, very remote and so very, very inaccessible. And obviously, everybody here is very anxious to get their hands on real life samples. This is totally understandable. But until the samples return from Mars, you are having to make do with analogs. Can you explain a little bit more, Anne, about analogs? What exactly are analogs and how are they used in a laboratory for research such as yours, for example?
That's a very good question. In fact, as you said, we still do not have samples from the Martian surface. The same for Venus, for example. That will be even more tricky to have some. So what we do in the laboratory on Earth is to use what we call analogs. That means samples which are made of what we find on Earth and what we think would be the most representative of what is on Mars. And so it's based on our preconception of what is there Of course, we now have a good idea of what is made up of the surface of Mars, but we do not know the details. And so our analog are our best definition of what we think it is.
Fascinating. And I think also you can create conditional analogs where with pressure chambers and so on, you can actually try and create environmental factors that are similar. For example, when we're talking about exposing her rocks to radiation to see what happens.
Yes. And so that's something that we did in Roadmap. We used analogs, but in environment which are very similar to what is expected on Mars. And for example, one of the experiments was to use a wind tunnel in which the dust would be placed on a sandbed and then wind would blow in the tunnel. And the tunnel is in conditions which are close to the pressure which are found on Mars, so very low pressure. So in this wind tunnel, we could reproduce some of the conditions which are expected to happen on Mars.
And how fast was the wind going?
Oh, I don't remember the exact numbers.
I was hoping for a massive, great big number, gazillion of kilometers a second. I bet it was going very, very, very fast there. And what did you find?
So we find very interesting results. So, for example, some are related to the depth of dust which can be lifted. So you might think that the quantity of dust which is lifted is not directly impacted on the depth of the dust layer. And that's one of the things that we found, that in fact, no, it is impacted. So if the dust layer is very thin, this dust is not moved away by the wind. So that's one of the findings.
But that's very interesting. Okay. So once it's thick, then the top layer comes off more easily. Interesting. Okay. Thank you very much, Anne. That's fantastic. I really appreciate that description. It was very clear. Does anyone have any comments or observations to make to Anne? Yes, Fuen, what would you like to ask Anne?
Thanks, Anne. I have it's just a curiosity. So when you perform experiments with dust, how do you characterize the dust? I guess it's a similar composition of the real dust on Earth, on Mars, I think. But how do you characterize it?
So first, the analogs that we used are, in fact, commonly found on Earth, in the sense that you can buy Martian analogs. And we started from those. And indeed, because one of the things we wanted to investigate is the impact of the size of the dust particles, we first made sure that our samples were characterized in terms of size and size distribution. So there are a lot of different measurements that you can do to check the size distribution of your sample. You can have direct measurement of the sizes, but you can also have images taken of the samples to see the shapes of the grains. So a lot of, I would say, analytical inspection of the samples was done. So we knew what our samples were made of.
Don't you also have data coming back from the rover with the probe? You've got chemical profiles and other things coming through, physical data coming through, no?
We have some images from the rovers. And they are sampling the surface. So we have some ideas, and that's how you build your analog. So the one that you can buy, they are built on those measurements and observations.
Excellent. Thank you very much for that clarification. Super. Good point, Fuen. Thank you. Mirko, I'm going to turn to you. Your project was called CRADLE, or in full, Collecting Asteroid Orbiting Samples, Enabling a Safer, Sustainable and Autonomous Exploration of Asteroids. Now, we've been talking about dust, so I'm sure we're going to come on to the notion of dust from asteroids and that sort of thing as well, in the collection of that. But before we do, why this area of research, Mirko? Why did you get involved in this in the first place?
Thank you for the question, Abigail. In the end, since I started by study, I have to say, in space engineering, and my dream my master's, I always wanted to contribute in some ways to space exploration missions, to interplanetary missions. But in the end, my career, my research career brought me to a different direction at a certain point.
It often happens, huh?
Exactly. It's not really predictable at the end of the day, not as much as you want usually. But at the end of the day, I had this opportunity with this project to, let's say, take everything that I had learned during these years, especially related to dynamics and dynamics of small particles and debris in particular in my case, and I tried to apply it to a different field, and in particular to space exploration missions and missions to asteroids and comets and these smaller bodies in the solar systems. And so I tried to, let's say, transition a bit and apply what I had learned before into a different area.
But it's still relevant. I mean, the ability to understand how to interact with small bodies moving at great speed is also vital to missions as well, I would have thought. But anyway, let's go back to Cradle. What did it set out to do, your project? And I know you wanted to further our understanding of these environments, but specifically, what were you looking at?
Yeah, basically, when we started with the project, we thought, let's say if we can find a way to sample, let's say, material from these remote small bodies like asteroids and comets in a different way in which it has been done so far. One could ask, why would you want to do that? Before, missions that have done this, which are just a few, did it, for example, by landing on a body or touchdown, actually most often touchdown. But there may be some ways in some occasions where this is not possible. And for example, this can happen if the environment of the asteroid is a bit too challenging. For example, we may have a too rough terrain, or we may have a dynamical environment of the asteroid which is very challenging.
Like a lot of dust, for example.
There could be dust, but there could also be, maybe dust is not so challenging in this case, actually, but it is more the way the asteroid moves.
Okay.
Exactly. So because you don't know it before, it's very difficult to understand how actually the asteroid looks like from the Earth and how it moves. And there are very small bodies out there that actually rotates very, very, very fast. And it would be difficult for a satellite actually to touch on the surface of this body. And so we wanted to try to find different ways and different approaches to enable sampling from these small bodies.
Okay. And can I just ask you why? I mean, why don't we just leave them in peace, spinning around incredibly quickly in the outer regions of the vast space? Why do we want to know?
Absolutely. We could do that, but sometimes we are interested in that. And for example, I would say that we are especially interested in these small, fast rotating bodies, because these type of asteroids are actually small asteroids below 100, below even 50 meters. And these are basically the class of asteroids that are most common in the solar system, but are also the ones that are more probable to enter the Earth's atmosphere, for example. And so we want to know how they're made and what is their composition, because it could be useful also for us in understanding what they can do when they enter the Earth's atmosphere. And if you think about it, there is maybe 10 years ago, in 2013, I think, there was an example of this in Russia with the Chelyabinsk event. This was a very small asteroid and caused a lot of damage by just entering the Earth and doing a shockwave, basically, that caused a lot of damage and some injured people.
And I guess the better you understand the nature of the asteroid, the easier it is, or not easier, but the more realistic it becomes to try and deflect them. Is that true also?
Indeed.
Okay, excellent. And so can you tell me a little bit about what you actually did in the project then?
Yeah, absolutely. So what we did in the project, so first, as I mentioned before, we thought, so how can we find a different way to sample this without having to touch this body? So what we thought, together also with the Japan Aerospace Exploration Agency, which I was collaborating with during the project, say, why don't we try to shoot it with a projectile, right? And this is not something that we come up just one day, because, for example, JAXA, the Japan agency, already did it with the Hayabusa 2 mission.
Oh, is that the mission that I touched on right at the beginning? The tiny,
exactly,
tiny, that was the Hayabusa 2.
It was perfectly in topic. And actually, they did it. So they shoot an asteroid with a projectile to create a crater and study the crater. And so what we thought together, say, why don't we just take it a bit further and let's see if we can do and try to use this methodology to sample the particles that have been generated after this impact. And so what we tried to do was to model it and study it as much as we could with methodologies that are available to us at the moment. And so we focused on the different aspects of that we needed to put together to see if this is feasible. And so what we did, we modeled how the projectile interacts with the soil of the asteroid, and so how it creates the particle, and after these particles are created, how they move around the asteroid. So depending on the shape of the asteroids or the dynamic, how close is the asteroids, for example, to the sun, this will impact how they move. And then what we said we wanted to do was also to say, let's see how we can design a trajectory of the spacecraft around this body with which we can try to collect these particles while they're there, and try to take as many as possible, actually, to try to maximize our return for the mission.
So I guess you were sort of also modeling what the impact of this particular projectile would be on the asteroid, so that whatever was circling the asteroid to collect the result wouldn't then also get involved in some sort of collision or because I guess if they're very small asteroids and you're firing a projectile at them, they're going to move away.
It would have to be a very, very large projectile for them to move away. No, the projectile, it's small, maybe 10 centimeter in diameter.
Right, so you're not actually playing cosmic billiards. You're not... Okay, fine.
This has been another mission, actually, which recently, with NASA and ESA combined, they're still carrying it out. But the projectile would be smaller, about 10-15 centimeters, which is the one, for example, of Hayabusa 2.
Oh,
but
okay.
Depending on the material of the asteroid, it's sufficient to create a very large crater. For example, Hayabusa 2 created 15 meters 15 meters diameter crater.
With a tiny little projectile. It's just fascinating. Oh, really wonderful. Thank you very much. And do you have some findings to share? Do you have any takeaways that were particularly interesting because the project's terminated now? So what was the key thing that you want to take away with this or tell us about?
I think we found quite a few things in the end, because we studied which kind of asteroids would be more suitable for such a type of collection. And usually these are asteroids which are on the smaller side, let's say less than a kilometer, and not too dense, for example. And usually it would be best to do it with asteroids that are not too rocky. For example, it's a bit more of a sandy material, which is typically what we have seen in past missions, for example, but it is not certain. But also several takeaways, I think, from the project were the methodology that we used, and I hope this can be used in further missions and in analyzing and in giving possibilities for exploring these bodies further. And we actually, where I was at JAXA, we already did some preliminary analysis for the extended mission of Hayabusa 2, which will go to one of these very small asteroids, these small fast rotating asteroids, and will hopefully reach it in 2031, if I'm not mistaken. We'll see. Hopefully some of the results we obtain will be used for this mission.
Well, it would be fantastic. That's absolutely brilliant. I think one of the things that I'm hearing from all of you is how your work is feeding into the next mission and the next mission. So it's a continual building on and building up from previous research. It's fascinating. It must feel wonderful to be part of such a bigger whole. That's great. Does anyone have any questions for Mirko, please? Yes, Anne.
Yes, I was wondering if your method was only applicable to airless bodies.
Thank you for the question. And I think that what we mainly studied it's mainly applicable to bodies without an atmosphere. They have to be smaller, let's say asteroid size. They can be few hundred meters, but they can be some kilometers. But having an atmosphere would be way more challenging, because the motion of the dust would be way different, really, really different. Because if we don't have an atmosphere, it's a bit easier to predict how they will move. The dynamics is much simpler than if you have, for example, winds or some other aspects that could change their trajectory wildly, like in a body with an atmosphere.
Like Martian dust.
Yeah, exactly.
Like Martian dust. Well, listen, thank you so very much for your time. That was just wonderful. I really, really enjoyed that. It's sort of new horizons opening up there. Wonderful. Thanks a lot for joining me today on CORDIScovery.
Thank you very much. And thank you for having me in the interview.
Good stuff, Mirko.
Thank you, Abigail.
Thank you. Bye.
Bye-bye.
Bye-bye.
Bye-bye. Had fun listening to this episode of CORDIScovery? Follow us on Spotify and Apple Podcasts, and check out the podcast homepage on the cordis.europa.eu website. Subscribe to make sure that the hottest research in EU-funded science isn't passing you by. And if you end up chatting to someone about podcasts you're enjoying, why not name drop CORDIScovery? We've talked about lights being used to direct fish away from nets, development in personalized treatment to target cancer, and how surprised crows are by certain magical tricks. In our previous episodes, there'll be something there to tweak your curiosity. Perhaps you want to know what other EU-funded projects are doing to improve our understanding of the mechanics of space. The Cordis website will give you an insight into the results of projects funded by Horizon 2020 and Horizon Europe that are working in these areas. The website has articles and interviews that explore the results of research being conducted in a very broad range of domains and subjects, from megafauna to megabits. There's something there for you. Maybe you're involved in a project or would like to apply for funding. Take a look at what others are doing in your domain. So come and check out the research that's revealing what makes our world tick. We're always happy to hear from you. Drop us a line. editorial@cordis.europa.eu. Until next time.